university teaching, work with nonprofit and profit research organizations, and service with several government agencies. He's been the president and treasurer of Blue Ridge Torch Club, where he has been a member since 2010. He and his wife Ada have lived in Northern Virginia for 53 years and in Potomac Ridge since 2004, which was when Potomac Ridge was originated. Mike is no stranger to anybody. He's been involved in everything. You've seen him on the stage. You've seen him as a master of ceremonies in several events. He's been heavily involved in Potomac Ridge. If Potomac Ridge had a Hall of Fame, he would be in it. Without further ado, Mike Levitt.
Thank you very much. Let me start the electronics here. I assume that will turn on when my computer turns on.
First. Yeah, okay, got it. Yeah.
Welcome. Thank you for coming tonight. My name is Mike Levitt. I'm not a climate scientist, nor do I play one on YouTube. But I have had a layman's interest for many, many decades. Since before I put together a 6-session program on climate change nearly 20 years ago for my alumni association. This program is something this particular program is something I've long wanted to do for myself. I have a handout for people. Could I get a volunteer or two for passing it out? How many people do we have here tonight? Do you know? At any rate, there are 50 copies, and if there is anybody who doesn't get one, please let me know, and I will send you one over the PDF or something like that. I usually welcome questions as I go along, but I do want to keep to a tight time limit. So I would request that you hold questions until the end. If you have questions, please, you can note them on the handouts or however you want to do it. My goal tonight is not advocacy. To understand climate change skepticism, I need to lay out a map of what is well established, what is genuinely uncertain, and what the serious scientific and policy disagreements are. I need to clarify some framing up front. Skepticism here means something precise. Peer-reviewed, methodologically serious critiques, not political denial. The two are very different, and I will distinguish them in a little later. This presentation assumes that you can hold two ideas at once. We have a warming planet and a complex, contested debate about magnitude, mechanism, and response. I will move from physics to models to policy, roughly from higher certainty to greater certainty as we go along. Let's see, how are we going to do that? Yeah, that worked. A note on my tone. You will hear critiques of the mainstream position and critiques of the critics. Neither side is treated as infallible. The presentation will be in 5 parts. Section 1 establishes a baseline, what the scientific consensus does and doesn't claim. Without this, the skeptic's critique floats free of what it's criticizing. Section 2. Need to push the button down. Where presents the most scientifically credible challenges. Researchers who publish in peer-reviewed journals and push back on specific estimates, not the greenhouse effect itself. Section 3 goes deeper on model architecture, what general circulation models, GCMs, can reliably project and where their structural limits are, independent, again, of political interpretation. Section 4 is where the debate becomes explicitly about values, as well as facts, of course. The mitigation adaptation question, involves ethical choices about time preferences, intergenerational fairness, that no amount of additional data can fully resolve. Section 5 closes by mapping the debate space as honestly as I can. What is settled? What is active science? What remains methodologically open questions? And what is real policy uncertainty? My focus tonight is going to be serious scientific skepticism, peer-reviewed critiques, credentialed researchers. I'm not interested in what I call dismissive skepticism. The distinction among skepticisms is important. Without it, audiences might conflate a serious skeptic with flat earthers. Or they might think that all climate concerns are politically correct alarmism. Both of these approaches short-circuit good thinking. Another area that short-circuits good thinking is impugning motives. This applies on both sides. Serious climate scientists are not just feeding at the trough of government research grants. Serious skeptics are not just doing the bidding of energy companies and related research funders. Going down that road is political demagoguery and ends a serious discussion. And that's all the ranting I will do tonight. Let me talk about this dismissive skepticism. It includes denial of basic radiative physics. It involves cherry-picking short windows. It's not, oh boy. It involves cherry-picking short windows to erroneously demonstrate a point. It involves reliance on non-peer-reviewed sources, and it confuses weather with climate. This is not what we are discussing. It does not deserve serious treatment as far as I'm concerned, and we will not receive it tonight. On the other hand, we have serious scientific skepticism. This operates inside the scientific community. It accepts global warming, but it questions the magnitude of it. It questions sensitivity estimates. I'm going to be spending some time talking about sensitivity estimates. It questions attribution methodology, and this is also going to be somewhat important. Model reliability is always an issue, and that's an issue for scientists. And the economic frameworks used to justify specific policy responses are also a big issue. Yes, Jim, I am going to be talking about economics. For what it's worth, you should know that I consider myself to be in the serious skepticism camp. You can check whether I'm providing a fair presentation at the end of this presentation. So what does the scientific consensus actually claim? Before evaluating skeptical critiques, it's essential to be precise about what the consensus is. As precise as you can be in a half-an-hour presentation. Vague appeals to 97% of scientists without specifying the claim isn't very useful. The IPCC, I'll be talking about that a couple of times tonight. The Intergovernmental Panel on Climate Change is the most comprehensive synthesis of climate research. Its reports distinguish between virtually certain effects, extremely likely, and lower confidence. What did I do? Lower confidence findings. Consensus is not a vote. It's an assessment of where the weight of reproducible evidence points. The next slide will unpack what is in the consensus. The goal is to give skeptics the strongest possible target. A steel man, not a straw man. So, the important thing about the consensus is that it is demonstrated by multiple lines of evidence. The strength of the warming case rests on convergence across independent data systems, not on any other single measurement. This matters because each data set has its own biases, but they agree anyway. The bottom line is that human greenhouse gas emissions are the dominant driver, and continued emissions will lead to further warming. Temperature records, surface stations, ocean buoys, weather balloons, satellites all show warming since the mid-20th century. Earth has warmed 1.1, 1.2 degrees Celsius since 1850. The oceans have absorbed over 90% of excess heat. Ocean heat increase is considered one of the most robust warming signals. Antarctic and Greenland ice cores provide atmospheric CO2 records from trapped bubbles and other sources. The 800,000-year record from Antarctica shows carbon dioxide ranging from 180 parts per million during glacial periods to 280 parts per million interglacial periods. Any guesses as to where we are now? 420 parts per million. Global sea level studies integrate multiple processes: thermal expansion, glacial melt, and land ice loss. So the sustained rise of about 8 inches in sea level since 1900 confirms the overall warming signal. The consensus is that sea level rise is likely to continue for centuries. So, what is the criticism? I'm going to get a little wonky in this section and the next, but it's important for this kind of a presentation. If wonky puts you off, it might be a good time to get a cup of coffee. The researchers discussed in this section, like all scientists, should be evaluated on the merits of their published work, not their political associations or how their conclusions are weaponized in public debate. These critiques have real implications. For example, if the ECS, okay, that is one of my favorite, one of the acronyms we're going to use a lot this evening. Equilibrium climate sensitivity. And that means warming expected from a doubling of atmospheric CO2. This is the standard measure that climate scientists, if you have to have one number, it's the headline measure, the ECS. It's closer, so the question is it closer to 1.5 degrees Celsius or 4.5 degrees Celsius? The timeline for serious impacts lengthens considerably, and the cost-benefit calculus of aggressive near-term mitigation techniques changes. A lot more on this later. Engaging with these arguments carefully is not equivalent to endorsing them. Engaging with arguments is how science works. This section covers three areas: climate sensitivity estimates, attribution methodology, I'll explain that, and the use of paleoclimate analogies. Each area has mainstream positions and serious credentialed critiques. Climate sensitivity, ECS, the key uncertain number. As we just noted, the IPCC likely range is 2.5 to 4 degrees Celsius. That's considered the 66% confidence level, with a best estimate of 3 degrees Celsius. That means, by this estimate, our equilibrium, the final warming period, the final warmings after doubling of CO2 would be about 3 degrees Celsius. But I'm just going to say the number. Celsius should be understood. If you need a primer on Celsius versus Fahrenheit, come see me later. Sherwood was a researcher in 2020 who combined multiple lines of evidence, including paleoclimate data, observations of recent warming, and climate model results to refine the estimates narrower than the IPCC's range to, by a small amount, but with the same expected value, at the same 3-degree expectation. Lewis and Curry, this is one of the more important teams of skeptics. They use something called energy balance estimates. Their estimate is substantially less, 1.5 to 2.5 degrees. It's peer-reviewed, uses observational data rather than model projections. An energy balance estimate is based on the Earth's incoming and outgoing energy. Sunlight in, infrared heat out. They argue that the IPCC underweights energy balance constraints. It's a methodological disagreement, not a denial of physics. Lindzen's hypothesis is that tropical atmospheric convection, the movement of heat within the atmosphere, reduces high cirrus clouds as warming increases. This provides a negative feedback, and his research implies a ECS below 1 degree. Well, most observational studies have not found support for that effect at that level, but the mechanism that he proposes is real, not debated, and the debate is about its magnitude. Attributions.
Mike, may I ask a clarifying question?
Yes.
So you talk about 3 degrees, 2.5 degrees, 1 degree. So we're talking about some kind of change in the global average temperature over some period of time. Could you define that a little more specifically?
Okay, so the ECS, let's see. Does somebody have a copy of the acronym list? I have the best quick definition is
equilibrium, climate sensitivity.
Warming expected from a doubling of atmospheric CO2.
So that would be the increase in the average Earth's temperature from today?
The increase of the average Earth's temperature since the baseline started, which I believe was 1950.
Okay. Thank you.
So a 3 degree, when we talk about an expected value of 3 degrees, it's 3 degrees from 1950 to whenever the predicted doubling of CO2 in the atmosphere
A
takes
doubling
place.
from that same year.
Yeah.
Thank you.
So, attribution science uses fingerprinting. And this is the phrase that is used in that literature. Looking for patterns of warming that match greenhouse effects to distinguish human from natural causes. Fingerprint methods strongly implicate greenhouse gases, GHGs as it's sometimes abbreviated, as the dominant cause of post-1950 warming. Solar output has been flat to slightly declining since the 1980s, while warming has continued. This is the primary empirical argument against solar dominance, but mainstream science disputes the magnitude again, but acknowledges uncertainty in the effect of solar estimates. So again, the question is, how much does the varying of the amount of energy we get from the sun affect the heat that is reflected back out and captured by the clouds and wherever and warming up the atmosphere? Urban heat islands are an issue that has been raised many times by the skeptics. Urban heat island effects are also real, but empirically not very great. If data collection stations are inside or near cities, urban heat island-induced warming can inflate the observed warming trend above what would be a pure, quote, quote, greenhouse-driven signal. One analysis found that the effect exists, but is small. Definitely small, about 0.05 degrees in the global mean trend. Extreme weather attribution. This is where scientific findings are most varied. Heat wave attribution, in other words, the effect of human activity on increasing heat waves, is now on relatively firm statistical ground. Hurricane intensification attribution, on the other hand, is far more contested. The data is nowhere near as clear. Drought attribution is highly case dependent. Some droughts seem to vary with warming. Some droughts do not. Event attribution science is young. Critics argue that confidence in extreme weather attribution outpaces its analytical methods. The human fingerprint on global warming is well established, but the human fingerprint on specific regional phenomena and extreme events ranges from well supported to genuinely uncertain. The paleoclimate refers to the climate of the Earth during past geological periods. Since we cannot directly measure past climates, paleoclimatologists use something called proxy data, physical or biological signals preserved by signals, I guess I should say data, physical or biological data preserved in ice cores, sediments, tree rings, corals, fossils, etc., to reconstruct past temperature, hydrology, greenhouse gas levels, and changes in the state of the system. The paleoclimate is the strongest long-term evidence for CO2 and temperature coupling, that they go together. But it's a technically fraught area for making confident claims about the present. Ice cores, for example, show CO2 and temperature have been coupled for 800,000 years. That's a reasonable amount. During what's called the Paleocene-Eocene thermal maximum, this was a great time to be alive. This is about 55 million years ago, and the global temperatures rose 5 to 8 degrees over 20,000 years, with deep ocean temperatures increasing 4 to 5 degrees, and surface air temperatures 5 to 9 degrees. This shows large warming from CO2 is physically possible. But the current rate of CO2 increases approximately 100 times faster than the past events, which itself is a concern about ecosystem adaptation. But there are significant issues with paleoclimate studies. These climate proxies generate data with long intervals between observations. The main issue is that they typically average climate data over long periods, and this blurs or misses rapid changes, can misrepresent timing. and misrepresent the rate of past climate events. The low temporal resolution, the long intervals between observations, means that paleoclimate time series are intrinsically fuzzy in time. And this complicates diagnosing the rapid changes that we're particularly concerned with here. In Antarctic ice cores during the glacial terminations, this is a little anomaly that has been discovered and accepted. CO2 rises roughly 800 years after the temperature went up. Okay, CO2 causes temperature rise, but this time the CO2 rises 800 years after the temperature went up. The standard explanation is that changes in the Earth's orbit and tilt alter the amount and seasonal distribution of solar radiation reaching the planet. It first triggers warning, releasing CO2 from the ocean, which then amplifies warning. I mean, it's a positive feedback kind of loop. The bottom line on paleoclimate for me is that it strongly supports the physical reality of CO2 forced warming over long timescales. But temporal resolution, limitations, and other conditions means it constrains precise prediction of future warming. Just not a great predictor. So now I'm going to get to talking about the models. Model skepticism is the most technical area of the debate because it requires engaging with the actual architecture of the global circulation models. Models are widely accepted as tools for understanding the physical system. The same models are challenged as prediction machines for policy purposes. Again, the point is that you can have a simulation model that helps a scientist understand the nature of relationships, but when you actually use it to forecast, predict future states, you may run into some difficulties. Climate models work with, and here I'm going to talk a little bit about how the models work. They work with geographical grids of 30 to 60 miles square. And they go up a couple of miles into the atmosphere. So-called subgrid processes are the rain showers, the wind gusts, the clouds that occur inside each grid square. The model can't work directly with these subgrid processes. It uses simplified mathematical formulas called parameterizations to approximate their average effect. I had to practice saying parameterizations 3 times. Models are explicit implementations of known physical laws with parameterized subgrid processes. Understanding what is parameterized versus what is resolved from first principles is central to evaluating their outputs. The model database has led to a mix of outcomes. This section asks, what should a scientifically literate person believe about the information content of a model projection? The answer is nuanced. Higher confidence at global scales over long time scales, yes, but lower confidence at regional scales in near-term time windows. What climate models are and aren't. Models reproduce. There are 2 strong model capabilities. Models reproduce the 20th century global temperature record well when given observed greenhouse gases in what are called aerosol loadings. The concentration, the aerosols. Oh, that's right. Our new member knows all about aerosols. Tell me if I don't get this right, okay? The concentration of tiny solid or liquid particles, the aerosols, suspended in the atmosphere. Atmospheric circulation effects like the jet stream are broadly replicated across the models. So these effects are well accepted. On the other hand, there are some areas where there are weak relationships. Regional precipitation. Projections for specific regions carry large uncertainty bands. As previously noted, cloud feedbacks are the biggest known unknown. Contemporary models span a factor of 3 in their cloud feedback parameters. Ocean circulation patterns that produce decade-long slowing or acceleration phases are driven by internal ocean circulation that models simulate only statistically. Internal ocean circulation is just not well done at this point in the models. Finally, most models lack mechanisms for abrupt transition. So tipping behavior is underrepresented. Tipping elements such as the West Antarctic ice sheet and the Amazon dieback problems. Any questions, I can talk about them a little later at question time. They're largely absent from standard models because they involve processes that are currently computationally prohibitive to model fully. But they're important. Climatologists have said so. Mitigation versus adaptation. Is that where I am? Yeah. Mitigation versus adaptation. Now this, I'm going to leave the wonky stuff and get to a debate which turns out to be very interesting for other reasons. The mitigation adaptation debate is where the conversation shifts from primarily empirical questions to questions that are partly empirical and partly value-based, involving choices about whose welfare counts and over what time horizon. Definitions. Mitigation means reducing greenhouse gas emissions now to limit future warming. Adaptation means adjusting human systems now to cope with warming that is already committed or is likely in the short term. This is where specific empirical uncertainties from earlier sections feed directly into policy conclusions. A world with an ECS of 1.5 degrees and competent adaptation capacity looks very different from one with an ECS of 4.5 degrees and delayed mitigation. The next 2 slides present the strongest version of each major position. They're followed by a key ethical issue. So, here are the cases. The case for aggressive mitigation. Remember, mitigation is doing things now to prevent future greenhouse gas effects. The first effect is really something that I heard of, but I didn't understand at all until I started getting into this. Martin Weitzman is an economist who has something called a dismal theorem. Not a great word. It's an important idea in climate economics. His argument is that when future damages are potentially unbounded, or at least we have no way of setting the bounds, and uncertainty is large, standard cost-benefit analysis breaks down. The expected future cost of damages may be dominated by low probability catastrophic outcomes, even if predicted median incomes. I'm making a distinction between averages and medians. You remember that from your statistics course, right? Okay. The future average becomes almost incalculable, even if a predicted median is manageable. This provides a rationale for aggressive action that does not depend on assuming a high ECS. Uncertainty itself becomes a reason for strong action. Path dependency and carbon lock-in. These are 2 phrases that you hear a lot in the literature of climate science. Path dependency in climate economics refers to how Early choices in emissions, technology, infrastructure, and policy can lock in high carbon futures, high CO2 futures, making future low carbon shifts harder. Makes them harder. Even if better options emerge later, you build a coal-fired carbon plant. You build a coal-fired energy plant today. You want it to last for 30 to 50 years. You have just locked in 30 to 50 years of carbon dioxide emissions. So you don't want to do that so often. Delaying clean innovation now risks carbon lock-in, where switching later requires dismantling sunk capital amid rising climate changes. Co-benefits, very straightforward. They are benefits outside of the climate arena for aggressive mitigation. And they're increasingly well quantified. For example, the World Health Organization estimates that air pollution, not CO2 directly, from fossil fuel combustion causes approximately 8 million premature deaths annually. So if you cut back on fossil fuel combustion, not only do you improve the CO2, but you save lives. That's considered a co-benefit. Makes sense. The mitigation case is strongest when framed renewable costs declines have been faster than nearly any modeling group projected in the 2000s or 2010s. For example, the cost of solar photovoltaic systems fell approximately 90% from 2010 to 2032. So, the mitigation case is strongest when it's framed probabilistically. Even if you assign a 70% probability to moderate outcomes, the 30% tail of serious damage may dominate your calculation. The question is not whether the catastrophe is certain, but whether the bet against it is a smart bet. So that is, as I understand it, that's the case for aggressive mitigation. On the other hand, the case for adaptation first. There is a sense that their development reduces vulnerability, and that argument is empirically well supported. For example, death rates from extreme weather events, floods, droughts, storms, etc., have declined dramatically over the 20th century because wealthier societies have better warning systems, infrastructure, and emergency response. So, economic development is what you want to do, right? The marginal cost, and sorry to get, again, a little wonky here, the marginal cost of deep decarbonization is the strongest economic argument for adaptation. Getting from 80% to 100% renewable energy, or net zero emissions, requires technologies such as long-duration energy grid storage, green hydrogen at scale, direct air capture, green cement, green steel, all of which are not yet commercially proven at the required scale. The cost of the final 20% may be much higher than the first 80%. Technological optimism has a track record worth acknowledging. Nuclear power in the 1960s, the Green Revolution for food production, the internet, shale gas, all are transformative technologies that arrived faster and cheaper than projections. Energy costs are regressive. This is a fairness argument. Energy costs are aggressive. Aggressive carbon pricing, making carbon more expensive, may impose disproportionate costs on lower income households in developing nations unless the policy that does those things is really carefully developed. Developing countries that have contributed little to cumulative emissions are being asked to forego the fossil fuel development path that rich nations used. The problem of having a just transition is not rhetorical. It's a genuine policy design challenge. The adaptation first position does not require disbelieving the science. Its strongest version says, even granting the mainstream warning projections, the best policy mix under uncertainty may weight adaptation and innovation more heavily than aggressive near-term decarbonization because the cost-benefit ratio of the latter is less favorable than advocates claim. The importance of future harm versus current costs is the single biggest driver of policy disagreement. Future harm versus current costs. This yields the question, and it's a question for each and every one of us. And there's no particular right answer. How much do we value the welfare of people living in 2100 relative to people living today? Reasonable people can agree on the physical science and still disagree deeply on policy, because the disagreement is partly about ethics, not just about science and facts. The practical takeaway, if you want to understand why two economists both accept the IPCC work and reach opposite policy conclusions, the answer is often differing approaches to the current costs versus future costs. Changing that answer changes everything downstream. Let me give you an example. Okay, you are the administrator of the Bureau of Climate Policy. That doesn't exist. And you have $100 million to expend on projects around the country. How would you divide up the funds? This table simplistically illustrates the difference between approaches. Okay, adaptation first policies. Let's say that you are the administrator and you are adaptation first. You might want to take that 100 million, 90 million of it goes to fix current problems. You want to build seawalls on the entire Atlantic coast for $90 million. But you'll give 10 million for future problems. You will lower the internal combustion engine number of internal combustion engines by 10%. 10%, that's good. Mitigation first policies, on the other hand, would switch those numbers. It's an example. I want to put $10 million into current problems. That means I'll build a seawall on Martha's Vineyard. But $90 million is going to go to the future, and with that $90 million, I want to ban internal combustion engines by 2035. So these are both policies with discrete, clear differences in outcome, depending on how you feel about future versus current costs. Of course, that's the world isn't going to be that clearly separated. Both of those could be continua. You could pick something in the middle, 50 million and 50 million. But the point is the example. Just about through. Where does this leave us? I want to talk about the landscape of credible disagreement. This is not a single spectrum from alarmist to denier. At this point, that should be clear. Someone can be mainstream on physics, a critic of methodology, and an outlier on policy, or any combination of those. What the presentation has not argued is that all positions are equally well supported. I hope that's well understood. Dismissive skepticism is poorly supported empirically, period. But there is more legitimate disagreement than most public coverage suggests. A useful, if stringent, test for calibrated thinking on the matter: can you state the strongest version of the position you are most skeptical of? If not, you may be engaging with a straw man rather than an actual argument. My final slide coming up aims to leave you with a map that I use that you might want to use in thinking about climate change. The first area is what is settled. I put this in quotes. I'm not talking about the science is settled kind of thing. I mean, settled does not mean beyond all conceivable challenge. It means the evidence is so convergent from so many independent sources that the probability of the consensus being substantially wrong is very low. Active scientific debate is where most of the serious action is now. The ECS magnitude, the magnitude of the sensitivity, cloud feedbacks, the role of variability among models. These debates are happening inside the IPCC process, in peer-reviewed journals, and in working groups. Methodological critique. This is also ongoing. It covers concerns that are legitimate research questions. You might need an advanced science or engineering degree to participate, however. Then there's genuine policy uncertainty. This is the most underappreciated area in the public debate. Two people can be in full agreement on physical science modeling and sharply disagree about the optimal carbon price, or the pace of transition, or the role of nuclear power or geoengineering, for example. The practical implication of this map is this: the appropriate approach, as far as I'm concerned, to thinking about climate science is neither follow the science, no further questions, nor the whole thing is a hoax. It is understand which of these areas a particular question belongs to and calibrate your confidence in the answer accordingly. My closing thought: a well-calibrated view holds scientific confidence and scientific humility simultaneously. Confidence that warming is real, human-caused and consequential. Humility about the magnitude, the differences in regional impacts, and the best policy response. Both attitudes, confidence and humility, are required. And the failure to hold both is the root of most bad climate thinking and unthoughtful policy. Thank you. If somebody could find a way to turn on the light, I'd love to be able to see people a little better. So this is a time for questions and comments. Jim.
Hello, thank you. So
Okay, so you talked about your parameterizations and you talked about uncertainty. But I know in the finance world they distinguish between risk and uncertainty. So risk is something that you can actually estimate. So you say, according to this parameter model, you have a 90% chance of some outcome. And you can actually think about that and price that as if it were some kind of, as if it were, you know, a model. Uncertainty is where you can't even model it, where it's just unknown and not even able to put it into a model. So when you use the word uncertainty there, are you talking about actual uncertainty, or are you talking about these probabilities that are risk?
I'm talking about the risk. I was using the term in a more generic sense than in a specialized sense. I was talking about uncertainty between 1.5 degrees and 4 degrees. You know, if that's our 66% confidence interval, that's an uncertain, that's a level of uncertainty. So I'm talking more about the risk that, as you define it in the finance world.
May I follow up on that in that case?
So if we're talking about risk then, rather than uncertainty, so that risk is actually priceable. You can actually set a price for it. And it's the same thing with these sort of these mitigation versus adaptation models too. So you can price those out as well and have like a continuum of mitigation policies and adaptation policies that utilize that risk in order to do cost-benefit analysis of each, right?
Very much so, very much so. That is exactly the way it would work, with one important caveat. There's probably more, but one that I presented, which is that dismal theorem, which makes it difficult to calculate the cost as risk, times outcome. It blows up a little bit at that point. So, yes, sir. Can I pass you the microphone, please?
First, thank you very much for what's really been a stimulating presentation. I think all of us feel a little bit as if we've stepped in front of a fire hose and have gotten an awful lot more information than we can totally process. But question, in the larger sense, we have now, over the past decade or two, seen large changes in public policy toward the family of issues which you have discussed, in particular the last two administrations. Many of us have felt that the United States was taking this issue of mitigation versus adaptation and making political decisions that were an active agenda much more than the rest of the world. What's Russia doing? What's India doing? What's China doing? What are the other major contributors to the climate, the world climate, doing in ways that will affect the outcome? Aren't we tilting at windmills if we characterize our own policies with our own mindset that don't take account of the fact that other countries aren't paying as much attention?
I couldn't agree more. The level at which I was talking, if you applied it directly to American policy, America first, and don't think about anything else, that would be a disaster. If you believe that a mix of adaptation and mitigation is a good solution, and you know exactly what proportion of what, it becomes the interesting question, but a mix of those policies is a good way to behave, then perhaps we ought to be selling that internationally instead of removing ourselves from the conversation. But that's a question that goes, I think, one or two steps beyond what I was trying to do in this presentation. What I was trying to do is demonstrate that adaptation is a reasonable component of the mix, and that the skeptics that I'm talking about are reasonable people who need to be listened to in the context of a discussion. So the best example, you may have heard that last summer the Department of Energy published a working group paper that was essentially authored by the most prominent scientific skeptics. Department of Energy, sometime in July. Good paper, nicely written, it was criticized by a working group of scientists who represent the consensus. Their response was entirely reasonable, readable, with a little scientific help, and the dialogue was worth paying attention to if you want to get into it that deeply. The only point that I was trying to make in that context was that discussion is important and it's real, and people who minimize it, and there are plenty of people on both sides who say, no, you don't want to have anything to do with those other guys, they're sort of missing the boat. But I'm diverging from your point entirely, but I agree with your point, and as sort of one level above on the policy area. Anne?
Well, I want to give one perspective of history. When you go to Greece, it's quite arid. At one point, they cut down all the trees, trying to survive, with no plan what to do with when the trees were gone. So they've had to live with the consequences. It's very hard when you're in survival mode to think about what happens when. I think we're sort of in that state. I've come to the conclusion that we can't turn back. I mean, climate change is a done deal. We're not going to be able to turn it around, at least in the short term. So how do we deal with what we have? And that probably might be something that should drive policy. I don't see a lot of that kind of policy thinking going on right now. Am I wrong?
I think you stated a very good argument for the adaptation first approach. And one reason that I don't think you have seen very much in the way of people articulating that as policy is that my perception of what's going on in the world, Jim, you pay attention to these things, I'm sure there are plenty of other folks who pay attention to these things, that the people who run the agencies who need to make those policies don't think in those terms. They may think in the same way that you do. For example, that we need to fix problems today. We need to fix the problems that we've got right now and worry less about the future. They wouldn't say that, well, it's a 20% adaptation first and an 80%. I mean, it just, how do you think about those things? But I haven't heard people speaking in these terms from those agencies, those bureaus, those departments that are supposed to be thinking that way.
I got a comment on that one. Yeah.
So, this morning, our Secretary of Treasury, Scott Bessent, made a talk about global climate change. And he made, there's two things that I understand now, the points that he made. So one of them was, we should not be focusing on mitigation, we should be focused on economic development. And now I kind of understand that as an adaptation first type of modeling that he was doing. But the second thing that he was doing was he was saying we can't really prove that man caused this global climate change. And so his approach was what I think is one of the most common arguments against climate change, and that is that it's a part of a natural cycle, that climate changes goes through these cycles where it goes warmer and cooler and things like that. But you had mentioned earlier in this presentation that some of those models that measure the length of these long-term climate cycles are not easily measured. And that is undoubtedly true. However, the models that they have, that they use, are talking about periods of time that are tens of thousands of years. And what we have now is a global climate change that happened over a period of 250 years. So the difficulty of these cyclical models really make a big difference between tens of thousands of years and 250 years. So it doesn't really reduce the value of those models. I guess what I'm asking.
I agree with your characterization of Secretary Bennett's comments as adaptation first. And I agree with, I think, what you're saying about his claim that we can't really prove. Well, science has a tough time proving. Science is supposed to be pretty good at disproving and sort of getting rid of all of the crud so that the only thing that's left is the thing that you say, I haven't been able to get rid of that, so this is what I think is true. Okay, so I'm guessing that Secretary Bennett was not thinking very much along the lines of what science is really good for. But let me just make a point about the data streams. You're right, the long-term data streams are hard to use, but the shorter-term data streams are better than that. They're fuzzy, but still pretty good. So for example, there is one collaboration that has created 2,000 years of climate data using proxies up until the point where we had accurate thermometers. Okay, so the proxies are pretty good, you know, the tree ring kind of thing. We're not looking at fossils over 2,000 years, but we are looking at things that we actually can measure. And it really, I mean, proving. So what, the data is pretty clear. It bumps along for about 1,800 years and 1,850 years, and then it goes up. Again, those converging lines of data go up. Now, does that prove anything or disprove anything? Not by itself. Not by itself. That's what the model ensembles tried to do. Oh, by the way, there's those data streams where, let me turn my back to you and do the graph. It goes like this from 2000 up until about 1850, and then goes bouncing on up. This is called, I love it, the hockey stick graph. It's like, you know, you have a hockey stick, but lying on its side. So the shaft is long and relatively straight, but the blade, the thing you hit the puck with, that goes up at a particular end. So it's called the hockey stick graph. I love it. So the hockey stick graph has been the focus of an awful lot of work to say, is the data accurate? Can you narrow the uncertainty boundaries within each of the data points? You know, if you're in the academic business, you can, you know, write 15 papers on the question of how you model to, you know, to change the uncertainty from that to that. So this is what I mean by this is the ongoing research, methodological within the scientific community. It permits you to be skeptical of the early numbers, whatever the early numbers say. Hopefully that there are people who will build off of that. But I'm not disagreeing with anything you said, I'm just really amplifying it. Other questions? Everybody wants to go home. Bill.
I assume that you've been following this subject for a number of years, and I also assume that the IPCC has been publishing their report for a number of years, maybe 30, 40, I don't know, something like that. Have you detected any trends in the evolution of scientific consensus in that body? Or do they, in effect, every year say the same thing?
Interesting question. I hadn't thought about that. I started paying close attention. Okay, the most recent, in 2023 is when it was published, was the 6th version, number 6. I started paying attention to it around number 4. The reports are big. They have executive summaries that are big. The summaries of the executive summaries are big. I mean, these are big reports. The technical, usually there's a technical report accompanying policy issues. There have been, to the best of my knowledge, and again, I started off by saying I'm not a climate scientist. There may be things going on under the covers that I'm just not aware of. With that caveat, I would answer your question by saying I have not detected very much difference in their various bottom lines. You get differences in the data sets that they use. They add to them. You get more and more groups around the world running the models. At this point, you can run some of these models on a very popular, a very personal workstation. I mean, to do them well, you need supercomputers, but you can get a sense of what they do from relatively lower cost equipment. So there are more and more people involved in this. Number 7 is in preparation. There are working groups that are preparing for that right now. I don't see any reason to expect any big differences there. Here's a political statement from me, and I'll throw it out, take it for what it's worth. I don't see that the IPCC people pay much attention to the skeptics and their work. I didn't see it in number 6, and I have no idea what it'll be in number 7. So if they're not responding to criticism, and I may be wrong on this, I haven't looked at it that closely. You?
Would you buy an electronic vehicle car?
In Potomac Ridge, they charge you $50 a month to plug into the garage space.
I should have said other things being equal.
Other things being equal. I don't spend $50 a month on gas these days. So, okay, but the point is a very good one. I would not buy an electric car at this point. I drove a hybrid for quite a few years, and now I'm not driving a hybrid, and I hope my next car is a hybrid. But here's the problem. You're going to hate me for this, Hugh. My reason for wanting a hybrid is that new hybrids are more powerful than their gas equivalents. That, if I got a Lexus, just pull something out of the air, if I got a gas-only Lexus versus the gas hybrid Lexus, and this isn't the plug-in hybrid, if I could go faster and still get good mileage. Now, my wife won't let me go faster, but I could. Murray.
Hi, Mike, and again, to echo someone already, thanks so much for a great presentation. It seems to me, and this, I guess, is sort of obvious, but it's been a long evening, and but this whole issue hits different countries in different ways. In our country, for example, the Navy has been examining for years the impact upon its ports and its ships. Russia, however, wants the ice melt in the Arctic because it gives them an additional shipping lane, I guess, to the Western Europe. I think it's Bangladesh, they lose how many acres every year because of arable land because the ocean takes it back. So it's really hard to find a universal worldwide problem because everybody looks at it differently. So thank you.
Yeah, 2 points there. Yes, there are very global differences in the effects of global warming, without any question. And the models don't do a great job helping us understand what things are going to look like in the Indian Ocean versus what things are going to look like in the Gulf of Mexico. So, yeah, I was being careful about that. So the point, but the first point of okay, tell me the first point. It's a long night.
No, first the Navy has been
Yes.
studying for years the effect upon its ports and its bases.
Right. The Navy has been paying attention to these issues for 30 years, as far as I can tell. They really care about that. Part of the problem that they have in Bangladesh and some of the smaller Pacific islands is that the sea level rise is in the bank. It's not going to be changed anytime soon, and by soon I mean in the rest of this century. So what do you do? Do you go for adaptation, or do you go for mitigation, hoping that you can reduce greenhouse emissions, you can reduce ECS, the sensitivity number, below the 4.5 high 66% level? That sounds like an adaptation problem to me. It sounds like if we're not going to lower the sea level around Bangladesh, somebody needs to come up with good plans for what to do with the people who live on the Bangladeshi coast. This is the ultimate question in adaptation. If you have your $100 million and you're trying to work in Bangladesh, how much are you going to put into moving villages one at a time, 10, 15 miles inland? Or are you going to work on reducing the number of internal combustion engines driving on Bangladeshi streets? I mean, these are the kinds of trade-offs that you have to make on policy. There are many more political issues, by the way, that go into the mitigation and adaptation that I don't have time to go into, but you've identified a key adaptation question.
So, speaking of mitigation versus adaptation, so this also is a response to the comment about China and Russia not really being part of this whole global climate change universal thing. But in China, they're actually moving rapidly towards renewable energy, sunlight and wind. And I think what's happened is when we think of mitigation and adaptation as sort of being dichotomous, and in addition to that, so you had mentioned one thing, that in a cost-benefit analysis, the costs were hard to estimate. But in most cost-benefit analyses, it's the opposite. It's the costs are easy to estimate, and the benefits are hard to estimate. And I think that in the whole mitigation strategy, they're undervaluing the future potential of renewable energies. So, for example, they have already shown that wind and solar power for generating big electricity generating plants is actually cheaper now than fossil fuels. It's not cheaper for your home, unfortunately. But what I'm saying is that I think that the mitigation strategy is undervaluing the renewable energies and the potential of that.
I'm not going to disagree with you. I think those are important considerations. If you throw in the costs to upgrading the North American electric grid to accompany renewables and the different operating characteristics that wind and solar have compared to a fixed plant that is just turning out electricity at a predictable rate. The network, the grid, has to be adjusted to that. And when you add on to the grid issue, the power demands of new computational issues, the electric grid in this country has some major challenges. I'm not arguing with your point about costs taken by themselves, though. That is absolutely right. The costs of solar photovoltaics are really a lot lower than anybody would have predicted 15 years ago. And I remember that because in a program that I put together, that's what they were trying to predict, and they were all wrong. I mean, solar, wind, it simply was bad predictions no matter which side of the fence you were on. Okay.
Just a simple one. There's a group of the skeptics, and which is the skeptics of everything, meaning including science, of course. And there's a universalist, I guess, whatever you call it. I discussed a little bit with some of those people. They don't care from the onset of our planet. Then we have the architectonic time, the 3.5 billion years when this separated, our Earth began. Then what happened? How many glaciations between there, the Paleozoic, which is about 50 million years ago, there's been 4, and then the last glaciation was close by, which is about 50,000 years ago or so. They said it will continue. They said this is an evolution of nothing but the planet. It's not going to be a Venus. It'll be the hottest planet of all. Eventually we'll get there because it has the greatest greenhouse effect of any other planet. So we're going to go there no matter what we do. So some people say that. Skepticism.
Yeah, this is a skeptical argument, and it is a basic argument. It doesn't particularly enter into the literature because how do you fit, a 10,000 year future projection into the modeling that's going on now? So it doesn't enter into the scientific literature. It's a very good question. For myself, as something of a skeptic, I'm not willing to wait around for the next glacial period. Anyway, I think I'm going to call it quits. Thank you so much.